I'm Eric Scheidley, and this is Astronomy Fundamentalized, Lecture 17, Cosmology and the Fate of the Universe. In this lecture, we'll discuss the cosmological principle and investigate what is known and unknown about the structure and evolution of our universe. There is a branch of astronomy that I have mentioned previously that's known as cosmology. Cosmology is the study of the structure and the evolution of our universe. In a sense, it is endeavoring to answer the great mystery of where our universe came from and ultimately where it's going. It suffers from a extreme difficulty of observation. It's certainly true that when we use telescopes to look out in the universe, our observation of stars and galaxies is limited by our ability to see. And certainly it's true that we've managed to see quite far already using the Hubble telescope and the other tools that are available to us. Nevertheless, our vision from the surface of the Earth is limited by all of the constraints of observational astronomy. It's also true that the universe that we're looking at is only the universe of today. It's very difficult for us to think about what the universe might be like in the future, in the past, without some sort of generalizing principles that we're going to hold as our fundamental axioms of the study. These two ideas formulate what is known as the cosmological principle. The first of the two is homogeneity. The idea here is that the universe is pretty much uniformly dense with matter, and dark energy. The reason why we make this assumption is because if there are regions in the universe where there happens to be some remarkable clumping of matter and energy that we can't have no access to, we can't make some observation of it, then that'll throw our entire cosmological study out of whack. And so we have to make the rather ignorant assumption that the universe is homogeneous everywhere. Now, certainly, it's not like we don't have evidence to suggest that this is probably the case, but nevertheless, it's one of our assumptions in cosmology. The other is isotropy, the notion that the universe is the same no matter where you view it from. That astrophysicists on some alien world billions of light years away would observe a universe that has the same properties as we view here from Earth. That is, the Earth is not a special location, and in fact, there is no special location in the universe from which to do cosmology. We make the assumption, and a rather vain one, and certainly a questionable one, that the Earth is a perfectly legitimate location in the universe to be doing cosmology. The idea of homogeneity of the universe is certainly supported by our experimental evidence. We look up with our telescopes in the sky and we take a survey of all the matter that we see. And here's an example of distribution of galaxies. See, the distance goes all the way out to 1,000 megaparsecs, and the density of galaxies becomes sparse. Well, this simply is recognized or can be demonstrated to be a limitation of our telescopic view. But closer in, we see that the galaxies are more or less spread uniformly throughout all of space. Certainly, there are features here, fine structure to the universe, like the Great Wall that previously been identified, and in fact, there are voids in between. But the distribution of galaxies appears to make roughly a sort of grayscale pattern everywhere in the universe, or at least in the universe that we can see, and that gives us our notion of homogeneity. The idea of the idea that the universe is isentropic, suddenly unable to say the word, the notion that the universe should be isotropic means that it should be the same looking in every direction. Well, Olber's paradox is a notion that is of great interest, or was initially of great interest to cosmologists, because if the universe is infinite and unchanging, then that means that there are an infinite number of galaxies in the universe, and in absolutely every direction you look, there should be a galaxy. And in fact, there should be so many galaxies in an infinite universe, an infinite number of galaxies in principle, that the sky should be lit up all the time, not dark as it appears when the sun is down on the surface of the Earth. So this is a strange paradox. If the universe is infinite and unchanging, then the sky should be uniformly bright, but it's not. So the only conclusion that we can draw from that is that the universe is neither infinite nor unchanging. The thing about Olber's paradox as well, and probably the best piece of evidence to undo it, is that we can't exactly see the entire universe. The idea is this. If the universe is larger than the time that it's taken for light to travel from distant objects to Earth, then we would not see the light from those regions in the universe. Consider the inset diagram here on the lower right, where Earth is viewing light from let's say two galaxies, Galaxy A and Galaxy B, that are very distant from Earth. In fact, they're 13 billion years away from Earth, which is nearly what we refer to as the age of the observable universe. So light from A and light from B have traveled for 13 billion years in order to arrive at Earth. In fact, according to this experiment, it has taken them the entire lifetime of the observable universe in order to arrive at Earth. Any star or galaxy or event that takes place to the left of A or to the right of B is so far away that any light that's created by those processes has not yet had sufficient time to arrive at Earth, so it does not contribute to the light that we see in the sky. The basic principle to take away from this is that there is a part of the universe that we cannot see because the light from that region in the universe has not had sufficient time to get here. That's why frequently you'll hear me refer to the observable universe. That is because with our telescopes we can only see into space as far as the universe is old. And as of today, the best distance that we've been able to measure, according to redshifts and so forth, is 13.7 billion light years, which means that the universe, so far as we can tell, is 13.7 billion years old. Now, because this experimental measurement is subject to a tremendous amount of error, it's actually so that the age of the universe is somewhere from 10 to 20 billion years old, but 13.7 is the best estimate we can make, and there is significant uncertainty in that measurement. Certainly, evidence that we have for the notion that we live in a changing universe is Hubbles Law. Recall that the observation of redshift in galaxies, which is in fact how we know that the universe is 13 billion years old, roughly, is that as we look out into our universe, the further we look away, the faster galaxies and galaxy clusters are moving away from us. Hubble recognized this law and was able to make this very familiar graph where the recessional velocity of a galaxy is graphed as a function of the distance to that galaxy measured in megaparsecs. And so we see the stars arrange themselves on a line which indicates that the velocity with which a star travels in kilometers per second, or galaxy travels in kilometers per second, is proportional to, or linearly in fact, proportional to the distance to that galaxy and in fact to the edge of the known universe. So from this line, we get the slope of it, which gives us the constant of linear proportionality, Hubble's constant, which tells us that the velocity is about 70 kilometers per second per megaparsec of distance measured from the surface of the Earth. The interesting thing about this is where we get our age of the universe prediction, because 1 over the Hubble parameter would be equal to the age of the universe, which, as I've already said, is 13.7 billion years old, and according to Hubble's observation of the redshift, the universe is expanding. The thing about the universe being infinite is that we now recognize that in order for the universe to behave the way it appears to behave according to our observations, it need not be infinite. An interesting thing about our universe is that, yes, every direction we look in, all of the galaxies that we look at seem to be redshifted. It seems to indicate that everything in the universe is traveling away from us. If we were to adopt a very conceited position and say that the reason for this is that we are at the center of the universe, we would be drawing a conclusion that has failed in every other instance that's been used in astronomy. For example, the notion that the Earth should be at the center of the solar system fails ultimately to explain observational results. The same is true for saying that our Earth is at the center of the universe and that the universe expands away from us. In fact, what's true is that the universe has no center. It's now our current understanding that every point in the universe expands outward from every other point in the universe constantly and everywhere in space. The way to understand this, to imagine that the galaxies are in fact in the universe as if being on the surface of a balloon. Here we imagine that the universe is the surface of a balloon, but I'll put the caveat here that the surface of the balloon is two-dimensional. The universe is three-dimensional. The trouble is, we can't talk about the way space-time behaves in three dimensions without using mathematical equations. The reason for that is that you cannot imagine four-dimensional space-time. We'll do a little exercise here. Many of us remember from our math classes in school the XYZ coordinate axes. If you take a piece of paper and draw the XYZ coordinate axes, one of the things that you'll try to do when doing that is to make sure that you draw them so that they appear to be perpendicular to each other. That is, you would draw them at right angles. Now, as you draw it on a flat piece of paper, it won't have right angles between the lines that you draw, but you'll draw it so that it looks like a 3D drawing in perspective. Another way to do this is to take your thumb, forefinger, and middle finger of your right hand and hold them perpendicular to each other, making an X, a Y, and a Z axis. In order to explain the curvature of space-time in this context, we would have to add a fourth axis, an axis that was perpendicular to the other three. So just take a moment and try to imagine how you would insert an additional axis, that is additional to X, Y, and Z, that would point in some very definable direction and yet be perpendicular to the other three. Take a moment to think about that, but I'll tell you, it's impossible for your mind to conceive of dimensions higher than three dimensions. This doesn't mean that it's not possible for us to do mathematically, and in fact, Einstein did just that with his general theory of relativity, where he predicted that space and time are combined together in such a way that space-time is curved in a higher fourth dimension. The interesting thing about this is that this space-time curvature is, for want of a better term, the cause of the phenomenon of gravity. And so it's impossible for you to measure things in four dimensions. So in order to visualize our universe, we'll imagine that it's the surface of this balloon. And the coins that have been stuck to the surface of the balloon are like galaxies. As we inflate the balloon, the surface of the balloon gets larger, in roughly the same way as we make the suggestion that our universe is getting larger. As the surface of the balloon gets larger, we see all of the coins surrounding the central coin getting further and further away. So from the point of view of the central coin, all other coins are getting further and further away from it. And that makes sense. We could just as now say, yeah, that's like being on the Earth with everything in the galaxy moving away. But observe this from the point of view of one of the other coins, one of the pennies, for example. If you view from the perspective of one of the other coins and observe the distances to each of the other coins as the surface of the balloon expands, we immediately recognize that the distances between all of these are getting larger. They're getting larger, the inter-coin distances, if I can call it that, are getting larger from the perspective of any coin. And so therefore, light emitted by any one of these coins, if they were galaxies in our real universe, would be redshifted according to that expansion. So all of the galaxies in our universe are essentially receding away from each other as the universe itself gets larger. It's the space-time that's expanding, not the physical extent of the universe. There's another interesting aspect to this curvature of space-time in this balloon analogy, and that is that if you lived in one of these coins, it's like it's a galaxy. You live there and you wanted to travel around in the universe. If you set off in any direction that you choose, in what you believe to be a perfectly straight line, you would travel completely around the balloon and come back to where you started. This means that the universe has no edge. You cannot go to the furthest extent of it and step over some line into a mysterious void. It would not surprise me at all to find that most of us think about the universe as a bubble expanding. Well, if that's the case, then the bubble that's expanding has a center, and there's an edge as it expands outward into what is a great mystery as to what the universe would be expanding into. We now realize that this is not the case, and in fact, the universe has no center, but is uniformly expanding away from every point in the universe simultaneously, and also we recognize that the universe has no edge, just as the surface of a balloon has no edge. Notice that if we wanted to talk about where was the previous arrangement, or what was the previous size of the universe, we have to look backward in time, and that the center of the balloon is not anywhere on the surface of the balloon, but is in fact in the balloon's past. And as we'll find, the same is roughly true for our universe. The curvature of space-time has another important effect, and that is it adds an additional redshift to the galaxies in our universe that's not associated with their velocity. Certainly, as galaxies recede away from us as the universe expands, the light from them is redshifted. But it's also true that as light travels through the universe, in the great distances between galaxies, perhaps on its way to a telescope on the surface of the Earth or in orbit around the Earth, the space that it travels through gets larger and larger and larger. Since the light is an electromagnetic wave that has a wavelength and a physical extent in space, as the universe expands, so does the wave. So here we have a wave drawn on the surface of a balloon, and the balloon expands. The wave starts out with a short wavelength and is blue, and as it expands, the wavelength gets longer. The wavelength is associated with the color, and as the wavelength gets longer, the wave gets redder. This is called cosmological redshift, and it's the redshift associated with the expansion of the universe and will turn out to be a very important tool for cosmologists. Another important observation that's been made about our universe is that there is, everywhere that you look, in every direction, a cosmological microwave background radiation. It turns out that there's some light spare left over in the universe that's just flying about this way and that, and in every direction that you look, the wavelength of that light, and thus the frequency of that light, is roughly the same and has a spectrum, which is here on the lower right, that looks almost identical to our black body spectrum. And in fact, the entire universe itself has radiant energy in it like a black body radiator that we discussed earlier in the course when we talked about how stars, as hot objects, produce electromagnetic radiation. So there's this cosmic microwave background radiation, and it is associated with a very, very low temperature indeed. In fact, according to Wien's law, the temperature of the universe is between 2 and 3 Kelvin, which is indeed a very, very low temperature. The explanation for this low temperature is that this radiation must have been produced when the universe was very, very young. At that point, the universe in principle would have been very, very hot during its creation, and the light would have had a very short wavelength. As the universe expanded, the wavelength of the light extended and extended and extended as it became more and more red and then into the microwave region, until finally it's the very long radiation that we view today. Radiation with a long wavelength as a consequence of the expansion of the universe. If this is true, it means you extrapolate backwards, the universe must have began its life very, very small, very compact, and very hot. When this idea was originally proposed, it was balked at by astrophysicists of the time and was jokingly referred to as the Big Bang. Since that time, experimental evidence and really good physics has come to the conclusion that this is in fact probably the origin of the universe, or ultimately the origin of the universe, where our universe came from. The experimental evidence gets greater and greater all the time. And the Big Bang, which originally started as a joke, is now the accepted cosmology of the universe. Our universe originated in a tremendously hot, compact object, which then expanded to the size that it is today, and so far as we can tell observationally, will continue to expand in the future. The trouble with the cosmic microwave background radiation is that when we look off in all different directions, the background radiation seems to be very much the same. The cosmic microwave background is very, very uniform everywhere in space. The trouble is that there are points in space that are now separated by about 13 billion light years. They're very, very far apart. So we might expect that there would be non-uniformities in the temperature of the universe. Why is it that parts of the universe that are so fantastically far apart would appear to be in thermal equilibrium? That is, to have the same temperature by association. The answer to that is the notion of cosmic inflation. The idea is that when the Big Bang occurred shortly thereafter, and by short, I mean really short. Take a look at the x-axis here. About 10 to the minus 36th seconds after the Big Bang, a very, very short period of time, the universe underwent a period of very, very rapid expansion. This rapid expansion accounts for the uniformity of the cosmic microwave background because before the inflationary period, all points of the universe would be very close together and be at equilibrium with respect to temperature, and then expand to a much larger size, but still maintaining their temperature, because the inflation would take place so rapidly that there would be no time for fluctuations to develop in the temperature profile of the universe. This is known as the inflationary epoch, and it plays an important role in our modern understanding of cosmology and the evolution of our universe. So if our universe was born in a Big Bang and had an inflationary period where it grew to an enormous size, and it has been growing larger and larger ever since, an immediate question that we have to ask is, what will be the ultimate fate of our universe? What's going to happen to it billions of years down the road? Now, certainly none of us individually has to worry about that, but it's a fantastic item of intellectual human curiosity to discover, or at least to make strong arguments about what the fate of the universe would be. If we imagine that there's a universe where all of the mass in it is expanding and everything's getting further away from everything else, and assume that gravity does not influence that behavior, then the universe should just go on expanding according to Newton's first law, that objects in motion will remain in motion in straight lines unless acted upon by a force. If there's no force to stop the universe from expanding, then it will expand uniformly forever. Einstein made note of this when he was formulating the general theory of relativity. He wanted to have a universe that did just this, expanded uniformly. The trouble with that was that as the universe expands, the force of gravity tends to draw it back together again. And so we should expect to see a universe that is decelerating as the gravitational influence of all those galaxies on each other pulls backward towards the Big Bang. And so we should expect to see the universe that slows down over time if gravity is a force that's acting. Einstein corrected for this by introducing a constant into his equations, which compensated for the force of gravity and added a little extra repulsive force in order to make the blue line look like the red line. Later on, he criticized this as being one of his greatest blunders, and that he should have relied on the universe to do what it does and go ahead and decelerate. So he died referring to this as one of his greatest blunders, and it turns out that he was wrong. It was perfectly legitimate, so far as we can tell, to put that constant in, but he wanted to put it in for the wrong reasons. And I'll come to that in just a moment. For now, let me say that we can imagine a universe where the mass of that's available to produce a gravitational force that would slow the expansion could in fact be large enough to arrest the expansion, to stop the universe from expanding, and turn it around and collapse the universe again back to the reverse of the Big Bang, what is sometimes referred to as the Big Crunch. Cosmologists have identified what this amount of mass should be in order to cause the universe to decelerate in Big Crunch. And it turns out that the observable universe that we can see today, including the luminous and dark matter together, has a mass only about 30% of what is necessary to cause the Big Crunch. So the Big Crunch line, shown here in green, is extraordinarily unlikely for the cosmological fate of our universe, and the gravitational deceleration of the universe, represented by the blue line, is more likely because of the low density of our universe. The thing is, though, that modern observations of our universe have indicated that it is not, in fact, decelerating, but accelerating. That as the universe gets larger, galaxies in the furthest distances that we can measure are moving with a velocity, and that velocity is getting greater and greater. That is, Hubble's constant is not constant as the universe expands in an accelerating way. Now, it's difficult to make this determination because the universe evolves over timescales that are much, much slower than the lifespan of even all of mankind. Nevertheless, the observational evidence that we have suggests that the universe is expanding. In particular, the cosmological redshift indicates to us that galaxies that are very far away, if the universe was decelerating, then when we look at galaxies that are very far away, we're looking deep into the past, and those galaxies should be moving with velocities faster than we expect, so that the universe today would be a decelerating universe, a universe which is expanding slower. But in fact, it turns out as we look deep into our cosmos that those galaxies are in fact going slower than they should be, which indicates that the universe is in fact accelerating as it expands. Why should the universe be expanding, and what does this mean for its beginning? On this graph here, we have the same arguments that we made before. We have a high-density universe in, I guess that's magenta, that would have so much mass that it would collapse. We have a critical density, which I did not include in my original graphs there, in purple, which is just the right density so that it decelerates to rest in an infinite amount of time and never collapses. A low-density universe, which seems to be the universe that we're living in, except for our observation, indicates the green, which is accelerating. Well, if we look at what these models of the future life of our universe say about the past, that is looking to the left of the vertical line on this graph, which indicates the present time, we recognize that a high-density universe, if that were the case, is much too young because its age would only be minus 5 billion years, a little over minus 5 billion years, and we can't account for that based on our cosmological evidence. And in fact, it's true that the low-density and critical density theories predict a much younger universe. The accelerating universe accounts for our cosmology better than any current model, and in fact, it's acceleration of the universe that's accepted as the observational fact at this point. Bearing in mind that there's great experimental error associated with these things and that observations are ongoing, but so far as we can tell, we live in an accelerating universe. If the universe is accelerating, there's got to be a reason for it. When it comes to Einstein's general relativity, it's not a problem. You simply take the constant that Einstein had originally introduced to counteract gravity, and you jack it up so that it not only counteracts gravity, but overcomes it, so that the universe is caused to accelerate by the influence of additional energy in the universe. Now, there's basically a law of conservation of energy that you're familiar with. If I take my pen and I throw it in the air, it goes only, it almost destroys stuff on my desk, but it goes only as high as its quantity of total energy will allow it to go, and then it falls back to the desk again. If our universe is to accelerate, there must be an infusion of energy. Energy that allows our universe to increase its kinetic energy as it expands without limit. Now, this energy is not energy for which we have any direct experimental evidence. So in the sense, just like dark matter, which we cannot see with our telescopes because it's non-luminous, we believe that the universe contains about 73% dark energy. This is the amount of dark energy necessary to account for the acceleration of the universe in our cosmological models. It means that there's energy which is not associated with gravitational potential energy and not associated with the kinetic energy of galaxies that is providing for the expansion of the universe. It is a very strange and mysterious theory, fraught with uncertainty in observational measurement and certainly with varying interpretation among modern cosmologists. But in terms of astrophysics and cosmology, it is the great question of the day. It is what we endeavor to discover about our universe. So we'd like to finish up the lecture with just sort of a history of our universe in general, in terms of everything that we know and everything that we understand. We begin here with this very lovely diagram all the way on the left, when quantum fluctuations in the fabric of space and time create the universe. Now, that's a very mystical statement, and in fact, don't even ask the question at a cosmology lecture about what happened before the universe existed, because the answer is we don't know. And in fact, up to about 10 to the minus 47th seconds after the Big Bang, or after the Big Bang took place, we have no idea what the universe was like, what the conditions were like. There is a strong belief that at that instant, at the very beginning of the universe, that all of the forces of the universe were unified, that the universe had a kind of elegant, simple symmetry to it, and that its expansion has broken that symmetry to create the profusion of physical laws that we see today. But that is difficult speculation, because information about what the universe was exactly like at that time can only be inferred from what the universe is like today. Nevertheless, about 10 to the minus 36 seconds after the Big Bang, the universe undergoes a fantastic inflation, where it grows in size very, very rapidly, and is completely devoid of any matter whatsoever. There's only light in the universe, no particles. About 300,000 years after that, the first particles emerge in the universe, protons and electrons, which ultimately coalesce to form atoms. When that takes place, the electromagnetic radiation that is the cosmic microwave background was produced. This is what is referred on this diagram as the afterglow light pattern. This is the light associated with the creation of matter in the universe, and it's what we see as the cosmic microwave background today. At this point, we go through a long phase from about 300,000 years after the Big Bang to about 1 million years later, when the first stars are created, about 400 million years after the Big Bang. The region in between is referred to the Dark Ages, sort of a humorous quip there. But the reason why is that if there are no stars, then there is no luminous intensity associated with the radioactive processes that go on inside of stars. Nevertheless, about 400 million years after the creation of the universe, the first stars form. And those stars naturally begin to exert gravitational forces on each other. And because of anisotropies and the way the mass is distributed in the universe, they form galaxies. About 300 million years after the first stars are formed, we see galaxy formation in the universe as the universe continues to expand. Notice that the cross-section of the diagram, as we proceed in time and see the formation of galaxies and planets and everything, continues on. The universe expands and continues that expansion. But of course, we've mentioned that the universe is accelerating. So about 8.7 billion years after the formation of the first galaxies, we have the formation of our solar system. The whole time, from the Dark Ages through to the present day, the universe is under the influence of a dark energy acceleration, and that expansion continues to accelerate the size of the universe. You may remember that at the beginning of this lecture, I mentioned that there is an observable universe outside of what we can see. That is, the universe is bigger than 13.7 billion light years. If we're correct about the notion of the universe accelerating, it turns out that the unobservable portion of the universe is getting larger and larger as it accelerates out of our view. It doesn't in fact come closer so that we can see the light from those objects, but in fact gets further away. This means that the observable universe that we have access to should be getting smaller and smaller. At any rate, this is the current cosmological picture. This is what we believe we know about the structure and the evolution of our universe. In this course, we've only been able to touch on the major topics. Certainly, everything that's happened here has a great deal of experimental evidence associated and was backed up with very sophisticated but accessible mathematics. If you're in any doubt about this cosmology of the universe, and I expect that you should be, then you should endeavor to read more about it and do your own investigation, understanding each of its aspects deeper and deeper. Astronomy, since ancients first looked up at the sky, has been an endeavor of mankind. Everyone is involved because everyone participates in what is the great mystery of our universe.